Okay, so, well, these are the references which I didn't include in the abstract, and we'll discuss the non-reference right at the end. And we'll just fix the notation as was written there. Okay, so, get a piece of chalk here. So the first thing I want to discuss is some motivation for the sorts of things we're going to be considering. By the way, I should say, so the main goal in this talk is to address what Mazur referred to as sort of one of the more subtle of the local deformation constraints, and this is related to finite flat group schemes. And this is sort of what, this is really the whole reason why we have to worry about finite flat group schemes when analyzing elliptic curves. Okay, so we'll start off as usual. So we'll have E over Q be semi-stable elliptic curve, and let P be an odd prime. And we'll see a couple of reasons later for why it's important that P not equal 2. And of course, what we want to show is that if we look at the Tate module representation of GQ on the Tate module of E, which we could think of as GL2 ZP, we want this to be modular. And there are a number of different definitions of modularity, which are all equivalent to each other by various non-trivial theorems. And the formulation that we're going to take and what we're doing is to prove that this representation is the representation coming from a suitable modular form. Weil's method for doing this involves several basic ingredients, one of which is the modularity of the residual representation. There are some other technical conditions, but in some sense, one of the most important ideas that makes his machine go is that he can interpret this in terms of analyzing certain rings, and this can be studied by looking at Galois homology. In particular, he has to analyze certain global H1s, which I won't discuss. They'll be discussed in later lectures. And roughly speaking, we want to study the order of certain global Galois homology groups. And there are a series of constraints on the cocycles that we consider on a finite number of decomposition groups, roughly speaking, corresponding to the primes at which E has bad reduction, together with the prime P. And what we're going to be considering in this hour is the local condition at P. And particularly in light of later work that Diamond did, it's really this local condition at P that's the most important of the local conditions. Well, before we can say much about the particular condition we're going to study, I guess I should explicitly state a couple of theorems which have sort of been underlying a lot of what's been going on before, but I don't think they've been explicitly stated, which is when you're semi-stable at P, how is this reflected in the Galois representation? Okay, so, and these theorems I'm not going to prove here. I'll either find references or include the full details in the notes. So suppose I give you an elliptic curve over QP, and suppose it has, for starters, either good ordinary or bad multiplicative reduction. Okay? And then if we consider the ZP deformation, and this is really why we care about deformation theory in the study of elliptic curves, of course, the Tate module representation is the ZP deformation of the residual one, which is the one that we've assumed is modular to begin with, then this has the following form. It can be put in a very convenient upper triangular form. Epsilon P will be our p-adic cyclotomic character on the decomposition group at P, and chi is some continuous unramified character. On the other hand, there's one other possibility from one other possible case if we have semi-stable reduction at P, and that's the supersingular case. Has supersingular reduction. So you have to be very careful when doing abbreviations. If you write SS for supersingular, you'll get confused if you write SS for semi-stable. So be a little careful there. Anyway, so if you have supersingular reduction, then things aren't nearly as nice. In fact, the residual representation is absolutely irreducible. And more precisely, if we restrict to the inertia group at P, this is isomorphic to what's usually noted the fundamental character of level 2, which maps the inertia group through its tame quotient onto fp squared star. And if we choose a basis for fp squared as a two-dimensional fp space, we get a representation. Again, recall the convention about finite fields bigger than fp. So this is residually absolutely irreducible. And then even the Tate module, let's say we tensor up to a field so we can really speak about irreducibility in a nice way, then the rho EP is again irreducible. Whoops. Non-dp. That basically follows, where's the eraser? That follows from the fact that the fundamental character, yeah, okay. Okay. So now the idea for the proof of this, I'm just going to briefly sketch, incredibly briefly. In the ordinary and multiplicative cases, you sort of prove it by hand. The ordinary case, you use a certain short exact sequence. In the multiplicative case, you use Tate curves. In the supersingular case, you have to use the theorems of Raynaud on finite flat group schemes. The essential point being, and I don't know of any sort of naive way of seeing this, the fact that this representation is irreducible is not something, as far as I'm aware, that you can sort of see by pure thought. You sort of have to really analyze finite flat group schemes in the supersingular case. Okay, so that's the end of that proof. Okay, so now we see that there are really two main cases. And we can see right off the bat that the ordinary and multiplicative cases are already distinguished insofar as we have a very convenient upper triangular form, and that's the sort of thing that Wiles exploits quite a lot in his analysis of the local case at P. And in the supersingular case, we can see it can be distinguished purely on the level of Galois representations, merely by the fact that we're absolutely irreducible, which is completely the opposite of what happens in the other two cases. So we have two main cases. So E over QP. So we group together if it's ordinary or multiplicative in the sense of its reduction type. And this is what Wiles calls the ORD case. And the other case, which is what we're going to discuss here, is the supersingular case in the sense of its reduction type. And this is what Wiles calls the flat case. And the problem is that even, it's sort of interesting to note, those supersingularities are relatively rare phenomena in the sense that few J invariants in characteristic P are actually supersingular, even if you only cared about proving the Taniyama-Shimura conjecture for ordinary elliptic curves for a very subtle technical reason, which comes up in Wiles' argument when he passes from the initial deformation problem to the so-called minimal deformation problem. Even if you cared about an ordinary curve, there are a few very special cases in which the minimal deformation problem suddenly acquires characteristics related to this flat situation. So therefore, even if you only cared about studying these curves, you'd still need the machinery that's developed to study this case, which may be too bad, depending upon your point of view. Okay, so the ordinary case, again, will be discussed in other lectures. As I said before, you simply exploit this very special upper triangular form when studying these deformations. I mean, together with other things characteristic of ordinary elliptic curves. But in the supersingular case, we're sort of stuck because we don't have a very convenient matrix form. This thing is two-dimensional. And so we sort of don't know what to do. We know we're residually absolutely irreducible. But what are you going to say if you're thinking about this ZP deformation? You look at the mod P to the n version. You're not going to say it's irreducible. That makes no sense because you're not over a field anymore. So you need some property of the supersingular case to sort of add into the absolute irreducibility to get a good local deformation problem. And that'll come from the following theorem, which also applies in the good ordinary case, except you don't have the absolute irreducibility of the residual representation at your disposal. And that's going to be quite critical for what you need in the supersingular case. So say we have good reduction. Then, and this is the whole reason we care about finite flat group schemes. Well, we could say for all m, though only certain m's will actually be interesting, this finite Galois representation, which we can equivalently think of as a certain finite flat group scheme of order m squared, this is in fact the generic fiber of a finite flat group scheme over ZP, necessarily commutative with order m squared. And the proof of this, well, there's not really much I can say about it. In the case when P does not divide M, you can in fact prove this using the criteria of Neronog and Shafarevich together with Galois descent of rings. But the most interesting case for us, which is when M is a power of P, or if you just want to consider the case of general M, as far as I'm aware, the only way to rigorously prove that you get a finite flat group scheme is you have to use Neron models and facts about abelian schemes and things like this. If there's a Weierstrass equation theoretic proof of this, I'd certainly like to see it. Let me just give an example of this in the ordinary case, because I don't want to write down the supersingular case. We've sort of described that a little explicitly. So suppose E over QP has ordinary reduction. Okay? So then the residual representation on the level of the generic fiber, the upper triangular form, well, it's going to be, you're going to have an unramified quotient. Let's say for simplicity, sometimes you'll have a trivial quotient, and the kernel will be another one-dimensional line with an action of the Teichmuller character. And the statement that this comes from a finite flat group scheme, so there's sort of some thing over ZP, which has this as its generic fiber representation, and you can define the notion of a short exact sequence of finite flat group schemes. And again, P is odd, so you'll have the short exact sequence where this will prolong to the constant group scheme Z mod P, and this will prolong to the group scheme mu P. So in this case, this is some finite flat group scheme, and you have some feel for it in the sense that you sort of know a couple of Jordan-Holder factors. Okay, and in the supersingular case, the situation, as I said before, is a lot more subtle because in some sense you can't really write anything down explicitly because we really feel happiest with one-dimensional irreducible representations rather than two-dimensional ones. Though one can certainly say things about the irreducible case anyway, as we'll see. Okay, so now this theorem motivates the following definition. This is 1.4. Okay, so if I give you any continuous representation of the decomposition group at P on the automorphisms of some finite abelian group, so then we find some finite Galois representation is what I'll just call it. We'll say rho is flat if there exists a finite flat, well, we'll just throw it in anyway, commutative, though it's automatic, group scheme G over ZP such that, well, the simplest way to say it is that if you consider the geometric points of this as some finite Galois module, this is isomorphic to rho. Alternatively, you could say that the associated finite commutative QP group scheme attached to rho is the generic fiber of some script G like this. And I should just add that script G is then unique by Raynaud's results, since the ramification index of QP, which is 1, which is luckily less than P minus 1, precisely because P isn't 2. Okay, one example, just to illustrate, this is an incredibly severe constraint. Suppose you considered omega squared. And suppose P was bigger than 3, so this isn't trivial or something silly, and this is not flat. You don't prove this by pure thought. You prove this by looking at the formulas of Oort and Tate, which classify generic fibers of flat things of order P, and you simply observe that omega squared doesn't appear on the list. But again, if somebody knows a proof that avoids that, I would certainly like to know. Okay, so you should always keep in mind this condition of coming from a finite flat group scheme is a very strong constraint. And in particular, Raynaud's theorem tells us we can think of finite flat commutative group schemes over ZP as identify them with their generic fibers. The problem is that in general, we don't really have a good feel for which generic fibers, which Galois representations actually arise in this way. So in some sense, the ones which come from finite flat group schemes, at least at this point, might seem rather difficult to study. Okay, so now to conclude this discussion, we see that E over QP is supersingular in the sense of its reduction type. Then we have two properties that we're going to exploit. First of all, the rho EP bar is absolutely irreducible. Well, in fact, assuming we were semi-stable, it already tells us that we were supersingular. And the property that we're really going to exploit in the deformation theory is this thing. So this is just theorem 1.2 up there. If I consider rho EP as a ZP deformation of rho EP bar, and this has the property that if I look at it mod any power of the maximal ideal, non-trivial power of the maximal ideal, this is now, see, the ZP thing is huge and infinite, right? But once I work mod p to the n, since my residue field is finite, now I have a little finite Artin ring, z mod p to the n, and so this is now a finite Galois, finite dp module. This is flat. Okay? So that's the main property. And it's the flat deformation functor is going to be a certain local deformation functor, which is going to exploit precisely these two properties. Whoops. Whoops. Okay, so now I should tell you what the flat deformation functor is. So I'm going to sort of formulate it in a slightly more general setting, simply because this might be needed in the later talks. I'm really not sure how those are going to go. But you should always keep in mind the case of this tape module where over ZP we haven't extended scalars in any funny way. Okay, so the general setup, we'll have O. This will be, think of ZP, this will be the valuation ring of a finite extension of QP. And K will denote the residue field, we'll call O mod lambda, where lambda is the choice of a uniformizer. I use this notation because that's the one that Wiles uses in his paper. I should point out, if the decomposition group notation bothers you, again, the only reason I'm using that is because that's what Wiles uses in his paper. And this is residue characteristic P. Okay? And now we're going to fix some rho bar from the decomposition group at P to GLN of K. I'm not setting n equal to 2 yet, just for conceptual clarity. This will be continuous. We'll assume it has cyclotomic determinant, and we'll assume that it's flat. Again, think of the supersingular case. I haven't assumed it's absolutely irreducible, again, because of this technicality that these methods will, in a few rare cases, be needed for the ordinary case. And lastly, we let d rho bar universal be the universal deformation functor. I'm not going to we'll discuss the representability in a minute, but at least as a functor on the category C sub O, complete local Noetherian O algebras with residue field K. Okay. So that's the universal function that we're going to consider. And as we've seen in Mazur's talk, deformation theory is related to Galois homology in the sense that we can think of the tangent space of the deformation functor as related to an H1. And so if you want to understand deformations, then one way to do it is to try to reinterpret things in terms of Galois homology. And since Weil's estimates involve keeping careful track of the orders of certain Galois homology groups, that can be, in some sense, understood by trying to count different types of deformations. And that's basically the strategy that we're going to take here. If rho bar is absolutely irreducible, then we have our representing ring, the universal R rho bar. Okay, and now we're going to define a certain, well, at this point, a certain sort of subset of this whenever we evaluate it. So for any A in CO, we'll define d rho bar flat of A. This will be the set of all deformation classes up to A with the property. Now again, A could be some huge infinite ring. We're interested in this sort of flat condition. So recalling what we saw up there on the second dot, we'll look at rho mod MA to the n. This is a finite Galois module, and this should be flat for all n. Whoops. Okay, so this is the certain subset that we're going to be interested in. And I should point out that based on certain properties of finite flat group schemes, it's equivalent to considering all large n, and therefore it's equivalent to saying that rho bar is flat in the Artinian case. Okay. All right, and once again, even though our main motivation is going to be in the supersingular case, we can still see, and we'll just remind you of sort of one example of this, which holds in both the supersingular and the ordinary cases. But again, the ordinary case lacks this special property residually of being irreducible. So for E over QP, with good reduction, then rho EP lives inside the flat deformation ring up to ZP of rho EP bar. Okay? And again, I have to emphasize this is this sort of thing, which is the way in which deformation theory will help us study elliptic curves, given that we're analyzing them through the Galois representations. I should emphasize, when you have additive reduction, the structure of these representations is far more mysterious. Okay, so now we come to the first really non-trivial theorem along this line of reasoning, which is the statement that this flat thing is actually a subfunctor of the universal one. What does this mean? All right, this means the following fact, which may not be, which is sort of not completely transparent, which is that if we have a map of rings in our category CO, so then any deformation up, any deformation up to A, we could think about as a deformation up to B simply by sort of shoving the entries of the matrix into B. In here, we have this flat subset corresponding to the deformations with this flat property mod powers to the maximal ideal. In here, we have this flat subset. And the statement is that this map actually takes that set into that set. And particularly in the case when A and B are infinite, but you sort of reduce to the Artinian case, it's not immediately obvious why this should be true. And it's sort of interesting that when Wiles first considered this problem, and he thought about maybe defining a functor like this, and he asked some experts what they thought about it being representable, and particularly in light of the fact that the flatness property is very difficult to describe explicitly in terms of the Galois representation, the reaction he got to the possible study of this, particularly its representability, was quite negative. But he prevailed. So so the remark to keep in mind is, in some sense, when you first see it, this is sort of amazing. But then you get used to it. Okay, and the way to prove it, you see, is to sort of not worry so much about the finite flat group scheme condition, because you're never going to write that down explicitly. But so this, I should say, this is due to his student Ramakrishna. or listed in the references. So the idea is to say, okay, let's ignore the flatness condition. Let's do something a little more general. We're going to define a property P, and it's going to be a property of finite dp mods, always with continuous action. It depends only on the isomorphism class. For example, the property of being flat. And we impose three more conditions. P is stable in the sense that it's preserved under the following constructions. You can take finite direct sums, subrepresentations, or quotients. Okay? This is some abstract property. For example, the empty property satisfies that, and then we get the universal deformations with the following definition. That's certainly not a very interesting case, but then we can define this thing just like we did in the flat case. All right, mod whatever power the maximal ideal, you have this property P, whatever it may be. Okay? And, oh, I should have added another condition here. This is a subfunctor, and if rho bar is absolutely irreducible, then it's representable. Okay? Anyway, so you define this, and then Ramakrishna shows by a very clever argument that these axiomatic properties alone are enough to verify Schlesinger's criteria, and in the absolutely irreducible case, verify all of them, and therefore we can get representability. And I should also say he uses these properties to verify this sort of a condition as well in this general setting. But then, of course, one has to go back and use one's understanding of finite flat group schemes, particularly the method of scheme theoretic closure, to check that you can take this flat property. Okay? So we actually have a flat deformation functor. Whoops. And in the case from a supersingular elliptic curve, this local deformation problem is actually representable. And again, since Wiles' global Galois homology estimates break up into a product of local Galois homology estimates, he's going to want to estimate some H1 attached to this deformation problem, again keeping in mind the connection between deformation theory and Galois homology, which was mentioned in Mazur's lecture. And so we're going to need to sort of somehow study these flat deformations very carefully and count them in order to, again, get, whoops, that's too high for me. And count them in order to actually compute the orders of the local H1, in our case, the H1 on the dp. And it's sort of remarkable that you actually get exactly the bound you need. And there's no a priori reason I can think of why everything sort of works out the way it does in the end. It's just magical. But anyway, so we have this nice functor, and now we want to study it a little more carefully, again, keeping in mind the motivation from supersingular elliptic curves. So now we want to connect this to a local Galois homology problem. And again, since the Galois homology estimates enter into the sort of the main structure of the proof, this is the sense in which this makes its way into the paper. Okay, so we're going to really think of ZP deformations in terms of their Z mod P to the n deformations. Right? We sort of look at a deformation, reduce it mod powers to the maximal ideal, and we're looking at various properties of it. And in fact, so therefore we'll consider, since we're operating in a more general setting, we're really in the end going to be interested in looking at O mod lambda to the n deformations. Okay. And more generally, let's just start off. Let's pick some A in our category, which is Artinian, i.e. a finite ring. Okay, for example, O mod lambda to the n. And we'll fix some deformation class with a choice of a representative, which is flat. And what we're going to be interested in doing is studying a certain local Galois homology group attached to this choice of rho. Whoops. Sorry. Okay, and so recall, as I mentioned in a previous lecture, that we can regard deformations of rho up to the dual numbers, which has an intrinsic A module structure. And we can identify that with H1 of dp against what I'll call ad rho. This is the adjoint representation, so just the matrices, capital N by capital N matrices with the conjugation action. And so we can identify these with each other. And the thing that's going to be critical to the way we're going to figure out, both sides look perhaps a little unmanageable. What we're going to do is reformulate what this is as an A module and then try to count its size in certain cases. So we have to recall the definition of an X module in a special case. So X1 of rho to rho as A bracket dp modules. This, we recall, can be thought of as you consider all possible extensions of rho by itself with X as A bracket dp mods. Again, continuous action on the X. And one has to mod out by suitable equivalence relation. This is actually a real set. In fact, it has an intrinsic A module structure, and we can identify it with these two sides. More explicitly, we can think of H1 of dp. There's just one way of looking at it. You could reformulate this in a lot of different ways. So this X module, at least as the level of sets, if we pick a cocycle representative here, well, we can think of an extension as sort of an upper triangular block matrix with a rho and a 0 and a rho. And this right-hand corner, you could think of, write it as C times rho. Rho is invertible, so you can construct an expression like that. Again, these are sort of functions of G here. All right, and conversely, any extension can be put in this form, and you sort of write the upper right corner this way, and you get a cocycle, and you sort of check everything's independent of choice of representatives, and it's an isomorphism of A modules. Okay. Well, now, you see, if you rewrite it in this way, the nice thing is, on the right-hand side, inside of this extension set, or extension module, is actually a, well, yeah, okay, leave this. Oh, I shouldn't have done that. I guess that's a bad idea. Sorry. There's a very special subset, which consists of the extensions for which X is flat. And it's that subset that we're going to be interested in studying. And again, this equivalence, the flatness depends only on the isomorphism class of X. So this is certainly going to be a well-defined notion. Okay. So inside, so as I said before, inside of the X1, we have what we'll call X1 flat from rho to rho. This is inside here. And this consists of the classes for which X itself, roughly speaking, X is flat. Again, A was an Artinian ring, so you don't need to mod out by powers of the maximal ideal. Okay, so these are sort of extensions where everything in sight is a flat Galois representation. Okay, so now what we're going to do is, in the case when P does not divide the dimension of the representation, so in the application n is 2, P won't be 2, we can write all matrices as the direct sum of a traceless matrix and a scalar matrix, and the Galois action is as you'd expect on the right-hand side with trivial action on the scalars. Then we can decompose H1 of ad rho. Well, any cocycle takes its values in the direct sum, so it's a sum of a cocycle in here and a cocycle on the other side, and everything behaves well with respect to co-boundaries. So we have this, and on the other hand, we have this identification with the X1. And as I said before, inside of here, we have this special subset of flat extensions, which is actually an A module, which is, again, not immediately obvious, but one has to check something about the group structure in here and properties of finite flat group schemes. So therefore, we identify that with a subset of cocycles in here, which we'll call the flat classes. Okay, those are going to be cocycles corresponding to flat extensions, and then its intersection with the traceless stuff we'll call h1 flat add row 0. As was indicated, I think it was yesterday, this traceless condition corresponds to fixing the determinant on the deformations. So that's where that condition comes from, because, for example, in the case of elliptic curves, we really only care about deformations whose determinant is the cyclotomic character. Because the underlying philosophy in all this is you want to understand a particular representation, you try to find as many constraints on your general deformations as you can to try to cut down the ring, and then hopefully understand more about the particular deformation you cared about to begin with. So now we can define, well, before I give the main theorem, let's give an example, rather simple sort. Recall this is the same thing as continuous HOMs from dp to A, not dp to A star. All right, A is an additive group. Okay, and so now we're going to consider chi in this H1, think of it as homomorphism, which is unramified. Okay, then you consider rho tends to 1 plus chi epsilon. This is some deformation of rho to A brackets epsilon. You can also think of it as an extension class given by a matrix of this sort. Okay, turns out from properties of finite flat group schemes, this is flat. How many of them are there? Cardinality of A. One checks. This is, in fact, an A line. Right, there's a single line inside of this A module. All right, this is, in fact, inside the sort of the flat deformations. Okay. It's interesting to note, as a consequence of the results we'll give later, at least in the case when A is O mod lambda to the n and rho bar is absolutely irreducible, only such chi will work. Yeah. So if you twist by a ramified thing, it can't be flat for the rho bars we'll be considering in the absolutely irreducible case. If anybody knows a proof of this in general, that would certainly be a little interesting. Okay. So now, I should have added up there capital N equals 2. Okay, so now finally we're going to state the main result concerning this flat deformation problem, and this is going to be, in fact, an exact determination of the size of the flat classes with values in add row 0. So flat deformations with determinant lifting the determinant of rho in the canonical manner. Okay, so this is the main result. Okay, so for n equals 2, p odd, p doesn't divide n, and we fix a rho. Oops, there's a flat deformation. So O mod lambda to the n. Okay, and say we even requires determinant to be cyclotomic. And we're going to make two assumptions on rho bar. We're either going to assume rho bar is absolutely irreducible, which is the case from supersingular elliptic curves, or else rho bar, well, has the other form. It's an omega chi 0 chi inverse star, possibly a split extension for some unramified character. Okay? Again, I should emphasize the only reason we care about this is because of the technicality that in a few special ordinary deformation cases, Wiles's minimal deformation problem requires him to consider some flat situation first. And, sorry?
What's the symbol in front of the chi?
That's an omega. That's Teichmuller. Sorry.
What does it mean? Is that the cyclotomic?
Yes, that's the mod p cyclotomic character. Sorry. Okay, then we have the size of H1 flat of dp, with values in add row 0 can be computed exactly. That's going to be the size of H0 of dp with add row 0 times the size of O mod lambda to the n squared. Notice, by the way, that this thing equals 1 if rho bar is absolutely irreducible or non-split. That's a calculation with centralizers. Okay, so this is the main result, that somehow we can magically calculate the order of this particular H1 for the add row 0. And this, again, this nuisance term is here precisely because in the special ordinary cases where we need to consider the machinery I'll mention in a minute, we're in fact going to have some split cases, in which case this might be not 1, so one has to keep it in mind. Okay, and just a remark, as I said before, well, in this case I'll just sort of, this is a very delicate estimate. The point is this is going to be, in the flat case, exactly the order that you need to make all of Weil's inequalities magically become equalities in the end. Okay, well, let me mention a lemma, sort of which one needs on the way to proving this, and this lemma is due to Ramakrishna, and the proof of this lemma illustrates all the essential methods involved in the proof of the main result. And so the statement is, well, first of all, we're going to specialize to the case where rho is absolutely irreducible, which really is most cases when we care about the flat condition, and n equals 2, etc. as above. And we'll make just a statement on the residual level. If I consider, if I consider the H1, and we'll work with the full adjoint representation. Passing between add row and add 0 row is sort of, it's just a little computational thing. It's really not the essential point. And so the H1 of the residual adjoint representation, its size is the square of the order of k. Whoops, this is not supposed to be there. Sorry about that. The idea being when you pass to the add 0, you've imposed one linear condition on this trace, and that sort of cuts it down, and that's why the square becomes a first power, and in this case, this is 1, so that's just a special, it'll wind up being a special case. This is a special case of that, but it's really the essential lemma along the way. Another way of saying this is, since, as I said before, this thing is actually a k-vector space, we can ask about its dimension, and this is just another way of saying its dimension is 2. So it's this two-dimensional thing. And again, this example 3.1 shows that in some sense one of the dimensions is sort of silly and easy. The other dimension is mysterious. But we're going to have to come to grips with that. Okay, one last remark I should make along these lines is, so this lemma is in fact also the essential step for actually computing the universal deformation ring in the flat case when we're residually absolutely irreducible. And so I'll just state what the idea is. And again, this is proven by Ramakrishna. This is really the main result in his thesis. And this result, which determines the universal deformation ring in the flat situation when you're residually absolutely irreducible, it produces a determination of the ring in a rather indirect manner without really giving you a canonical way to think about it. But then later work of Maser and Fontaine sort of made an understanding of this somewhat more explicit. So suppose we consider M is the maximal ideal of R rho flat. Again, rho bar is absolutely irreducible. So this thing really exists. Then this reduced cotangent space can be identified as a k-vector space with the H1 flat. This is general formalism about deformation theory. This says k-vector spaces. In particular, this lemma says this is two-dimensional. Picking a basis and using the completeness, we can get a surjection like this. And then Ramakrishna shows, so now in fact, he shows this is an isomorphism. So one's natural reaction to try, idea for how to prove this might be use commutative algebra maybe, but you don't really understand this ring very well from a commutative algebra viewpoint besides some formal properties. So Ramakrishna uses an amazing counting argument to show that this is actually an isomorphism. And you have to, in some sense, implicitly use sort of the idea of a p-adic analytic function, but I won't get into that. Anyway, So that's a determination of that ring, and that's critical in chapter 1 of the paper. Actually, let me just briefly indicate why this is so critical. So this is an isomorphism. And the reason this is so important is that, therefore, if P is the kernel of some section, so say this is a pointed ring, and I've given you an O deformation, okay, and so that corresponds to a map from that ring down, so you get a map from here down. Well, just by using the completeness of O and changing coordinates, you can assume its evaluation at some ordered pair of points in the maximal ideal. Check that. Change coordinates, so it's evaluation at the origin. So P is T1, T2, and in particular, P mod P squared is isomorphic to O plus O. It's a free O module of rank 2, which is by no means obvious by pure thought. And that's very important. But I don't have time to really indicate what Ramakrishna's counting argument was. Very clever, though, but okay, and so I guess that's for that remark. Okay, so now the problem is, if we want to prove this lemma, or even the theorem, we have to somehow count things. All right, we're not going to get this just by thinking about it. We really have to write something down. And so the problem for these proofs is to somehow study the size of this Galois homology space. Let's say in the case of the lemma. All right? Because again, you want to understand the deformation ring. This indicates, for example, already how an understanding of Galois homology can tell you something about a deformation ring. So you want to understand the deformation ring. You look at the Galois homology side. On the other hand, as I pointed out above, the Galois homology can be identified with this X space. Now, this is the whole reason we introduced the X1s to begin with. You see, the right-hand side is quite explicit. You're trying to write down short exact sequences of Galois modules. The unfortunate problem is you have this funny condition. Okay? And so somehow we have to write down elements on the right-hand side and figure out how many of them there are. So in other words, we will it's sort of indirect, but in principle it's completely explicit. Write down everything. Well, I won't do it here, but it'll be in the notes. I'll explain the method. Everything on the right-hand side, which is sort of amazing because you don't really think you can usually write down finite flat group schemes, because these rings with these co-multiplication maps, it's all rather confusing. But in fact, the miracle is that there's a way to do this. And this is a theory that was developed by Fontaine. And in the time that remains, I'd like to explain the idea behind what Fontaine did. So again, you really have to realize that it's, in some sense, an amazing thing that you can actually figure out the size of this, because in practice, when you study finite flat group schemes, or schemes in general for that matter, it doesn't proceed by writing down the rings. Usually you find some indirect way to study things and try to get away with as much as you can just by thinking about it. But in this case, there's no way, as far as I'm aware, of really figuring this out without actually writing everything down. And so what we're going to do is I'm going to explain a method that you can use to write down group schemes without being able to write down their rings. So this is where the references F and double F came from at the beginning. Double F stands for finite flat. Well, it's not really a theory of them in general. This is really, well, it's a theory of group schemes in a special case, but it's the general case of his theory. Okay. So just to simplify notation, so we'll let FFZP, this will be the category, finite flat commutative group schemes, over ZP with P power order. And we'll define FFFP in the same way, but just over FP. this is the category we really have to somehow understand, and it's a little mysterious at this point. On the other hand, so we'll just remark this is somewhat mysterious. This, on the other hand, this is not very mysterious. Well, it may seem so now, but I'll explain why in a minute, that it's sort of easy. The thing to keep in mind is the classical theory of Lie groups. You have a correspondence between connected Lie groups over the reals with finite dimensional Lie algebras. So in a sense, you could study group manifolds of a suitable sort via linear algebra, just by playing games with matrices and things like that. And so there's this very beautiful theory that works for suitable group schemes over suitable fields of characteristic P, called the theory of Dieudonné modules. And you can think about it as sort of a characteristic P analog of Lie algebras in characteristic 0, except you see group schemes in characteristic P have these funny nilpotent things in them, so the Dieudonné module really requires a bit more effort to define. But nevertheless, in our special case, the sort of analog between Lie algebras and Lie groups comes the following result. So you have an anti-equivalence of categories, which just means the things are contravariant. So if you like, you can make things into the opposite category, but that's really a content-free notion, so we're not going to bother with such formal nonsense. So we can think about finite flat group schemes in the following manner. They're going to be the same thing. They can be identified with ZP double bracket FV modules over this ring, which have finite ZP length. Okay? And we'll call this script M of G. Okay? The F and the V stand for Frobenius and Verschuebung. So those letters do have a meaning. And given an M here, we can attach to it a suitable group scheme here. This has a number of properties. You can read off properties of one in terms of the other. So some sample, so one illustration is the ZP length of this is equal to the order of the corresponding group scheme. Anyway, so the point is, we'll give an example now. You can play games with finite flat group schemes just by writing down these funny modules on the other side. And so you might want an example of, what is the Dieudonné module of some sort of standard group scheme. Or equivalently, let's write down some candidate Dieudonné modules, and I'll tell you what the associated group scheme is. And again, I should emphasize that the fact that one identifies a given group scheme with a Dieudonné module is not by using the definition, but just by understanding how you can read off enough properties of the group scheme in terms of the Dieudonné module, and then crossing your fingers and hoping that's enough to let you figure out what it is. So for example, so let's give you some candidates. So you could have FP. Just move this up here. So you can have FP, and you could consider, for example, the case where the F will act as identity, V will act as 0. You can consider F acting as 0, V acting as the identity, F and V both acting as 0. And in this case, the corresponding group scheme, here it turns out to be the constant group scheme Z mod P. Here it turns out to be the group scheme mu P. Here it turns out to be a certain group scheme called alpha P. Okay? Which we'll see more of in a minute. But the point is that this shows that if you look at the closed fiber, you really can play games with it using linear algebra. Unfortunately, okay, and so we'll just give this example, ramified case. Suppose you consider, just for the sake of ease, we'll work in a cubic extension, just because otherwise it's more complicated to write down the examples. If you consider the two factorizations of P, you get two different finite flat group schemes, but they have the same closed fiber alpha P, which one checks by a calculation. So passing to the closed fiber, you do lose some information. Okay, so these have the same closed fiber. Okay, so you do lose some information. Luckily, though, and now we're really at the sort of main result, which will wrap this up, well, second to last, fortunately, this passage to the closed fiber is faithful on maps. Okay? So in fact, sort of going from G to what I'll call G bar, this is faithful on maps. So I know this is proven by Fontaine, maybe it was proven earlier. Okay, so different maps induce different maps on the closed fiber, and therefore you should think of G as sort of being the same thing as the Dieudonné module of the closed fiber, which is the same thing as sort of knowing the closed fiber, together with perhaps some extra structure, whatever that might be, enough to sort of turn faithfulness into full faithfulness. And so now we have the main theorem due to Fontaine, which is, so suppose we define the following category, which we'll call finite Honda systems. This will be the category of pairs Lm, where M, is a ZP FV mod FV minus P mod with finite ZP length. L is some submodule. As a ZP module, it might not be stable under F and V, and you make the following two hypotheses. V on L is injective. The kernel of V doesn't meet the submodule. And the natural map from L mod PL to M mod FM is an isomorphism. Okay, so we define this category. And then Fontaine actually constructs a functor that associates any finite flat, any G in here, he associates, and the maps are sort of the obvious ones compatible with the data. So given a G, he's going to associate a pair, which will be the Dieudonné module of the closed fiber. And then using the fact that you actually have a full ring over ZP, he exploits that with his co-multiplication map to define a suitable submodule, which I'll call L of G. And he verifies using essentially the entire theory he develops in his p-divisible groups book. He can prove that, in fact, this satisfies these properties and that this is, in fact, fully faithful. All right, in the sense that it's a bijection on Hom sets, and it's essentially surjective, meaning every finite Honda system is isomorphic to the finite Honda system coming from a finite flat group scheme. And so, therefore, it is, in fact, possible to, instead of, you don't, strictly speaking, have a quasi-inverse functor, but that's not terribly important for what you want to do. You play games. You can talk about short exact sequences. You have explicit formulas for kernels and co-kernels of finite Honda systems. And so, therefore, this game of trying to write down actual extensions of rho bar by itself, well, you sort of use your knowledge about rho bar to understand a little bit about the corresponding finite Honda system, which is attached to the full ring that it comes from, since it's flat. And then you sort of study extensions of this Honda system by itself. And the point is, in some sense, it's linear algebra. It might be a little complicated because this ring is a little funny, but in some sense, you're playing games with finite length modules. And so therefore, in principle, this result makes it extremely plausible that you really could compute and write down all the possible extensions of rho bar by itself, which are flat, simply by transforming it into a question about finite Honda systems. So if you use this theorem, then in fact, you can carry out the calculation that Ramakrishna does, and you can, in fact, compute the order that you needed. Now, I should end with a little remark, which is this non-reference. So there's sort of it's sort of been said in a lot of places, this article of Fontaine-Lafaille where they do, I don't know, a lot of, prancing around and stuff on the whole article. And the problem is that it's sort of right at the end where Wiles needs to use this connection they make up. They construct lots of Galois representations of Galois groups of local fields, and at the very end they make a connection to representations coming from finite flat group schemes. More precisely, what they analyze is the problem of starting off with the linear algebra data, getting a group scheme, you get a generic fiber Galois representation, and they directly construct this as a functor without mentioning the G that occurs in between. Anyway, the thing is that the proof of all that machinery relies, the critical meat is in the book by Fontaine on p-divisible groups, and this short article of his where he sort of discusses the outline of the proof for this theorem. And in a sense, this is all that is really true. This is all that Ramakrishna and Wiles and Diamond actually use. The fact that you can describe the passage from the right side to generic fiber representations via some intrinsic functor is not needed. All they need to use is the fact that you have this explicit construction with some understanding of what it means. You know, this thing is the Dieudonné module. You know a little bit about Dieudonné modules, and so you can read off some stuff. So in fact, if you're interested, Fontaine-Lafaille paper has certain important applications, but if you're interested in understanding this work on the Taniyama-Shimura conjecture, you do not need to read the Fontaine-Lafaille paper, and even if you did, in order to understand this last section, you'd have to read the Fontaine book anyway. But the point is that the Fontaine-Lafaille paper itself has no logical relevance to this paper, to Wiles' work at all. So you should just keep that in mind. That's it.